We can break down a linear complex problem into two or more different subcomponents, allowing us to analyze each subcomponent independently and then combining the results to solve the original and lower issue. Take a look at this. Imagine that we have several inputs for a system, and as a result, we obtain several outputs. So consequently, we can add those outputs together to obtain the output of the entire system or the entire function. This is called the superposition theorem. And imagine that you were needing to measure the weight of a package, but you don't have a scale big enough to measure that thing. So you start by measuring each item of the bus separately and then add those weights together to know what is the weight of the whole package. Or picture a rolling wheel, which movement means the sum of the translation movement and the rotation movement together. In electric and electronic circuits, the superposition theorem is where common analysis methods are Norton's and Thevenin's equivalent circuits reset. So in this video, we're going to dive into that topic, and as usually, we'll take our time to get practical with an example so that we can all better understand the superposition theorem. My name is David from dodnatic, and let's dive into it. Alright, so in electrical circuits, the superposition theorem states that the voltage across the nodes is equal to the voltage generated when only the voltage source is connected and the voltage generated when only the current source is connected. In the other hand, it states as the current flowing through a branch is equal to the current generated when only your voltage source is connected and the current generated when only the current source is connected. So here we can see that we need to just focus on a single source at a time, while the other ones are set to zero. So what does set to zero actually means? Alright, so in the first case, for a voltage source, it means that we will need to replace it with a short circuit or using a conductor. And you know that theoretically a conductor has zero resistance. So from Ohm's law, if you want to calculate your voltage and you have a current and times a resistance that is zero, your voltage will be zero. And in the other hand, if you want to set to zero your current source, you will need to create an open circuit. Theoretically, an open circuit means that we're going to have an infinite resistance. So from Ohm's law again, if you want to calculate your current, you have your voltage over a resistance that is so big, you will have no current flowing through it. Okay, cool. So now let me have some examples done so that we can grasp this theorem better. Alright, so we were asked to calculate what will my multimeter display if I measure the voltage across the 30 ohm resistor in the sense that is written in black. Alright, so here we see that we have two different sources, a current source of 0.3 amps and a voltage source of 20 volts. So I'm going to redraw the circuit, but I'm going to set to zero one of the sources. So in this case, I will set to zero the 20 volts voltage source. And we already know that in this case, it will be a short circuit. So in the resultant circuit, we have two different arrangements of parallel resistor. So let me calculate that. RT1 is going to be equal to 96 times 32 over 96 plus 32. And it gives me 24 ohms. And for the second arrangement, we have that it's going to be equal to 120 ohms times 30 ohms over 120 ohms plus 30 ohms. And that gives me also 24 ohms. Okay, so let's redraw this new circuit. And in this case, we have a current source in series with two different resistors. So we need to calculate what's the voltage across the resistor RT2, since this is the equivalent resistance of the second parallel arrangement of resistor. And we know that when we have resistor in parallel, the voltage across the two of them or all of them is the same. So the voltage here by Ohm's law is equal to 0.3 ohms, that's the current in series, times 24. And that gives me 7.2 volts. And this is the voltage across the resistor R2 and also the voltage across the resistor of 30 ohms caused only by the current source. Perfect. So now let's go ahead and calculate what's the voltage produced by only the voltage source. So let me draw my circuit. In this case, let's set to 0 the current source, and it's going to be an open circuit. And in the resultant circuit, we can see that we have two different networks. So I'm going to focus only on the network below. That's where my 30 ohm resistor is located. So let me read out the circuit, and here we have a voltage source in series with two resistors. So first, I'm going to calculate what's the current. By Ohm's law, the current is equal to the whole voltage, 20 volts, over the equivalent resistor. In this case, is 120 plus 30. And that gives me a current of 0.133 amps. Awesome. So with this information, I can apply Ohm's law again to calculate what's the voltage across the 30 ohm resistor. And in this case, it gives me that we have 4 volts. But this 4 volts, it's the voltage if we measure the voltage across the resistor from positive to negative. I was reading here. However, if we take a look on the circuit above, we see that the sense of the way the multimeter is connected, it's different. So in this case, we will measure from negative to positive, and that is going to give me minus 4 volts. Awesome. So now that we have those two values, let's just, combine the two results together to know what's the overall voltage across this resistor. So we have the voltage is equal to 7.2 minus 4 volts, and that gives me a total of 3.2 volts across this resistor. Alright, so now let's compare this with my simulation. I have my setup here. So I'm going to be measuring the voltage across the 30 ohm resistor. So let me click on simulate here real quick. And let me click on this. Alright, so we see here the green line. Let me zoom in. Perfect. So we see that we have 3.2 volts. So it definitely seems that we did good. Thank you so much for staying until the end of the video. If you enjoyed the video, please don't forget to click on the like button or on the subscribe button. My name is David from dodnatic, and I'll see y'all in the next one.